Right, so welcome everybody for joining our April edition of our Everything Astronomy section. Thanks so much for always making time to join. It's good to have you. So we will start the section shortly. However, as we do it, you can just put your name or where you're joining us from into the chat, and just so that we know each other before the section starts.
Start. Okay, type in which episode.
Okay, so in the chat, we have Josiah. I think Josiah joins our sections regularly. So he says, hi everybody, this is Josiah from Nigeria. Happy to be here. Thank you so much, Josiah. We also have Terry, who is from the University of Ghana, and he says, thank you so much for joining too. And yeah, so thank you so much for joining. We also have Francis. And I know he's from Nigeria, and because he has also been joining our other section. So, guys, thank you so much for joining, and yeah, hope we will have a good time. So we have also enabled the live transcription, which means that whatever we do say will appear on the screen, and you can read from there. So that's also something you can check out for. Okay, so maybe we wait for 2 minutes and then we can start. Okay, so whilst we wait, if you have not introduced yourself, you can put in the chat just your name and then where you're joining us from, and then anything cool you want to add, you can do add. Okay, so Terry is asking that, can we play some music whilst we wait? We just have 1 more minute to start, so I think next time we can try to do that. Oh, it was supposed to be a private message to me. I'm sorry, Terry, for reading out. Okay, so this one. Okay, yeah, all right, so it's fine. So I'll just say again that welcome everybody to our Everything Astronomy section. So this is a section where we talk about astronomy among some other related topics at the end of every month. So last month we had one, and we usually have it at the on the last Saturday of every month. So this April too, we have this, and we happen to in the past have invited special guests, people talking about their research work, and then we have an expert also talk about specific fields like we have had in the past. So we have had somebody talk about exoplanet from the University of Leeds. And we have had, I think, Ghana's first female astronomer also give a talk in the past. So today we have Dr. Ama Brown Klutse, who is a senior lecturer at the Department of Physics, and I'm going to say more about her shortly. The theme for today's talk or section is the links between astronomy and climate change. This is quite interesting because it's one of the fascinating things that we can actually have to talk about. So as usual, apart from we talking about this, we also have a section where we'll talk about what's present in the night sky, and then we'll do a few astronomy news. So welcome everybody, and I hope you have a lot of fun today. So today I'm hosting the section with Jemima. So usually we do have Sarah, but I think Sarah should be able to join later today. But I'm Solomon Apeke, and I'm a science and astronomy communicator. And I also do work for a young space startup in Ghana called X Space Solutions, which I'm going to talk about shortly. I'm a research student at the University of Leeds, and yeah, I just like astronomy so much. So we also do have Jemima, who is the public relations officer for the Ghana Cancer Rocketry Championship. So we are going to co-host the section today, and she's also a student at KNUST. So Jemima, if you're there, maybe you can turn your video on and then just say hi to everybody.
Hello, everyone. I'm Jemima. I'm Jemima. I hope we all have fun here. I hope you all learn something new, and I hope you form connections and clicks among each other. Yes.
All right. So thank you so much, Jemima, for that. If you happen to be in Ghana, we urge you to visit the Ghana Planetarium Science Center, which actually has a planetarium, and the planetarium is just a dome-like structure where you go in there and you can have, depending on what show is given, you can actually get to feel that you are in space, and it's definitely a place that you should visit. So the main thing about the Ghana Planetarium is they also do promote astronomy and space science in Ghana, and they are also partnered with the section that we're having today. So do visit the Ghana Planetarium, and I'm sure you have plenty of fun. So like I said, there's a young space startup in Ghana called Xavier Space Solution, which is also helping to have this section. You can visit the website to know more about this, but like you know, all space startup would want to send stuff into space. That's what this company is also looking forward to do. And it's actually responsible for leading the Ghana Cancer Rocketry Championship. And at the moment, we do have experimental satellites, which we have built ourselves just to prove that concept that we can actually be able to develop our own stuff and put these things in space. Yeah, that's about our sponsors in general. So we don't have announcements. And what we do have now is we will go straight to what we have for today. So I'll just introduce briefly Dr. Ama Brown Klutse. Her affiliations are with the University of Ghana, and also the African Institute of Mathematical Sciences in Rwanda. She's currently a senior lecturer at the Department of Physics at the University of Ghana. She's also the lead author in Working Group 1 and a member of the task group on data support for the Intergovernmental Panel on Climate Change SIP Assessment Report. She is also a member of the scientific board of the International Basic Sciences Program of UNESCO. She is also an Ames Canada researcher in climate change science with Ames, Rwanda, and then Ghana. So she's been doing a whole lot of stuff in terms of climate change or climate, and to be interesting to actually have her to talk about this thing. And we believe strongly that she's the best person to talk about this thing, and that's why we do have her today. So thank you so much for joining, and I'll just hand over to welcome again, Dr. Nama.
Thank you. Okay, so thanks for having me, and good day, everyone. Do I have to Yeah, you have to unshare your screen. Good, thank you. So should I go ahead straight away? Okay. Okay, so I'm going to present a controversial topic linking astronomy and climate change. I would say it's a bit controversial because whenever we get new things or new ideas in science, becomes controversial until we have a complete understanding of the subject. So thanks to the Ghana Forum and the team, believe there's a good knowledge that goes out there. Okay, so just like 2 days ago, the University of Ghana announced my promotion to associate professor, and yesterday the social media was flooded. Yeah, so
Congratulations, congratulations.
yeah, thanks for this opportunity to present your group. And so we're going to look at it together, star formation and the gases that comes out of the gases. We look at the Earth atmosphere, we look at the climate and the greenhouse effect, and to understand a little bit about patterns in space and the other planets. Then we see the interactions. Okay, so this is a picture. The NGC 7822, this is a classification of star formation. And this is the picture I want to start with. And this is a star formation. And when stars are being formed, gases are released. And when stars die, gases are also released. Actually, stars are chemical factories. So gases that we have in nature are mostly produced from stars, especially the natural elements that we find on the periodic table. And a few of you that are already aware or familiar with astronomy, you know that we have about 400 million stars that get born or get formed every day. So per second, we have about 4,800 stars that get formed per second. So imagine, you can imagine it's out there in the celestial space. And the interesting thing here that which is the controversy here is that when stars are forming and also when stars die, they do produce a lot of gases. So as you can see in the picture, the bright colors are all stars that are being formed. The pink area is the area that is still forming. So those pink areas are still not matured yet, they're still in the process of forming. But the bright dots you see are the stars that are already formed. So there are plenty stars, and the gas spaces, those are gases that have been produced from the formation of the gases. And so if we're getting 4 million stars being produced per day, you can imagine how many gases or a day from the stars being formed, and also the same rates at which the stars also die, although they live for quite some time. Different stars have different lifespan anyway. Okay, so that's just the periodic table. Is the basic element that that we get from the stars when they form. So we get some carbon, we get hydrogen, oxygen, nitrogen, and magnesium, lithium, aluminum, helium. All these basic basic elements on the periodic table, we get them from during star formation. And this is where we come in. In our atmosphere, we have a mixture of gases. The atmosphere is the column of air surrounding the Earth, which I'll show you briefly. Column of air surrounding the atmosphere. And that column of air is a mixture of gases. And these gases are also in the natural elements that we find in the periodic table, that also get produced from star formation. So this is just a pictorial description of what I'm trying to say. It's a mixture of gases, so we can find nitrogen, oxygen, carbon dioxide, and methane. I mean, this is more than beyond the natural gas. These are some combinations as well. But then at least for the natural gases, we have neon, we have nitrogen, we have oxygen, we have carbon. That is part of, and hydrogen, part of what we have in our Earth atmosphere. And we know how the Earth looks like. It's one of the planets in our solar system. So the Earth just looks like that. The atmosphere of the Earth is just a thin line or an ocean of air. So the air, the mixture of air is what you have seen earlier on. But it's just the thin blue line you see is our Earth atmosphere. It's a very thin space around the Earth when you compare to the size of the Earth itself. But we can look at the atmosphere also with a division. It has layers, and the layers are according to the temperature and chemistry. Gases that we have in the atmosphere, and in temperature as we go from the surface of the Earth to the top of the atmosphere or beyond, there are different temperatures that you will experience when you move from the surface of the Earth and you're going up in the atmosphere. For example, in the troposphere, when you stand on the surface of the Earth up to about 10 kilometers in the atmosphere, we have the troposphere. Beyond that, we have the stratosphere. Above it, we have the mesosphere, and then the thermosphere. Then after beyond the thermosphere, we have the exosphere. That's when you go into the other space. So getting to other planets, the exosphere, the space between the Earth and then the other planets or other bodies of the terrestrial system. So moving from the surface of the Earth through the troposphere, temperature becomes cold, so it's warm on the surface of the Earth, and as you go up in the troposphere, it becomes cold. And then when you get to the stratosphere, it becomes warm. When you go to the mesosphere, it becomes cold, and then the thermosphere becomes hot, actually hot, and then continue to be hot beyond the exosphere. So just an overview of what the atmosphere is. You've already seen a mixture of gases, but then just for you to also appreciate the percentages of how these gases combine in the atmosphere. So nitrogen is the most abundant gas in the atmosphere. We also have oxygen being the second most abundant, and then we have so argon is in a very small percentage. Then we have the carbon dioxide, it's also a very, very small percentage relatively. Then we have other gases like water vapor. Water vapor is also a gas in the atmosphere, and it's also in a small percentage compared with nitrogen and oxygen in the atmosphere. But then these are, so these exist in the Earth atmosphere. So I'll show you also what exists in the other atmosphere. Some of these gases do not change in their quantity. So gases that do not change in their quantity, we have nitrogen, we have oxygen, we have argon, neon, helium, hydrogen, and xenon. They exist in the atmosphere, but they don't really change in their quantity. We have other gases that do change in their quantity. So they vary depending on certain situations, which could be the formation of stars, could be our activities on Earth, and we are going to go into that or debate on that. So we have the water vapor that varies or changes. We have carbon dioxide, methane, ozone, sulfur dioxide, nitrogen dioxide. So we have these gases that keep changing in their composition in the atmosphere, keep changing. And they have different effects in the atmosphere, especially when they change. So whenever there's a change in quantity or in the composition of the atmosphere, it means that any of these gas might have changed in its quantity or in its volume. I can put it anyways. So carbon dioxide is a greenhouse gas, as well as methane, as well as ozone, as well as water vapor in the atmosphere, and we'll talk about that. But ozone has some positive influence in the atmosphere. It protects us from the harmful ultraviolet radiation. It's an unstable gas. It's an unstable gas in the stratosphere, and we have nitrogen dioxide, which we get from combustion. So whenever there's we get smoke or burning, we produce nitrogen dioxide as well into the atmosphere. And once they are available in the atmosphere, they can cause acid rain, and that comes back to us on Earth. Okay, so I talked about water vapor. Water vapor is important also in the atmosphere because it supports or helps with cloud formation. Vapor, we can't have clouds to form, and eventually we can get rain or precipitation. So which means we can get snow, we can get hail, we can get any different type of precipitation because clouds can form, and they form from water vapor. So we need water vapor in the atmosphere so that we can have rain. And it also helps to move. Water vapor is the gas that helps to also move energy and other particles in the atmosphere around the globe, the Earth. But it is a major greenhouse gas, and we'll talk about that. We also have methane in the atmosphere, which is also a greenhouse gas. So the greenhouse gases that exist in the atmosphere or those that contribute a lot in the atmosphere are the water vapor, methane, nitrogen dioxide, we have the ozone and carbon dioxide. So they exist in the atmosphere. And they cause greenhouse effect. And just to also let you know what greenhouse effect is. So these gases that are available in the atmosphere as greenhouse gases, they prevent or they serve like blankets or a glass wall. So they prevent the Earth heat energy from escaping the Earth into space. So like the Earth as an object, or every object that gives us radiation, as in Stefan Boltzmann's law says, every object gives us radiation. So like your body will give off radiation, your phone will give off radiation, water, bottle, everything, even water will give off radiation. Same as our Earth system will give off radiation. And they do that depending on the energy that they have. And in Stefan Boltzmann's law, those who have done a bit of physics, Stefan Boltzmann's law says that they do that, it's the energy that they give off, or the radiation they give off, is equivalent to the fourth power, or it's proportional to the fourth power of the air temperature of the object. So the Earth, depending on the Earth temperature, it will give off energy. That is the radiation it will give off. And this energy, when it is given off, it means that when you have higher temperature, you give off more radiation. So depending on the temperature of the Earth, it will give off a certain amount of radiation. But then these greenhouse gases have covered, or they exist in the atmosphere, and they block the radiation from getting out of the Earth, or getting out of the Earth's atmosphere. And so the heat remains within the Earth atmosphere, or they trickle down back to the Earth. And this is the noise or the talking, the advocates about global warming. So you've seen that the variable gases are mostly the greenhouse gases in the atmosphere. Those are the gases that do change. And once they keep changing, it's possible, especially if they are not reducing, but rather increasing, they cause more greenhouse gases and they cause more warming. And we have evidence showing that the Earth climate or temperature has warmed, and it's warming very quickly. And when we use the past years to measure, we can see, though we see variability, you can see from the line that from industrial level. So when you compare that to the current year in our 2000s, you can see the temperature has been increasing. And these graphs, what is important about this graph is that the black one, the temperature that is observed, and then we have the red one, that is the temperature that's the warming that is due to human beings or anthropogenic actions. And then we have the green lines, that is warming or temperature due to only natural drivers. So if you can see that the human-driven temperature is consistent with the observed, what's the name, temperature. And the natural forcing or naturally forced temperature is rather going the other way around, goes a little bit lower in the negative anomaly. But the human-driven one goes completely observed, which means that we can say confidently that there's a major contribution of human activities or human forcing of the current observed temperature that we have it, and little influence is in the natural, as a natural driver. So the reason why you have to understand the star formation and the gases that are released from the stars and linking it to the gases in the atmosphere and those gases that can cause or are causing global warming because of greenhouse effect. It's also because we have these gases and our scientific knowledge hasn't reached the level of understanding the influence or the impact or the effects of these gases on our climate system. Our studies initially have shown us that astronomy we have astronomical effect as part of the causes of climate change, as well as the atmospheric composition. So we have talked about the composition as in the mixture of gases, which we get a lot from star formation, but studies haven't reached where, that is in planetary science, hasn't reached where we can confidently confirm that gases that's the 400 million per day stars that are formed and the majority of the gases that's released from there have direct influence on the Earth atmosphere. We still understand those in planetary science. I think last year, 2021 Nobel Prize winners, one of them that worked on planetary science, tried to do this kind of link and got a Nobel Prize on that. So apart from the stars forming, you know, our sun is also a star, but then other planets also do have different mixture of air, and I just want to bring to your attention a couple of them. So Mercury has no atmosphere, so Mercury has no gas on it, but we have Venus that has gases. So Venus has 96% of carbon dioxide. It has sulfuric acid, and of course, it's a very hot planet. It's bigger than the Earth. But what I intend to show you is the percentage of carbon dioxide that exists in Venus. Venus is not too far from Earth, of the planet Earth. We have the planet Mars, which also has almost 76% of carbon dioxide, has a little amount of water vapor. That is why scientists have studied and proposed that there could be life on Mars, because what we need is carbon dioxide, really, and water vapor or water. So once water vapor exists, it's water as air, it can be converted to on liquid. Human beings can survive on it. And once we have carbon dioxide, plants can also survive with carbon dioxide, and the two combination of some of these gases go through chemical reactions, and they can produce oxygen also. So which means that life can really exist on Mars. But again, Mars has a very wide temperature range. It can be as cold as -80 degrees Fahrenheit and as hot as 70 degrees Fahrenheit. So that is the only, I would say, disadvantage. Otherwise, there's a high potential that life can exist on Mars. Okay, you can just move. So even scientists have seen further that water once flowed on the surface of Mars. So, but that's another topic altogether. Jupiter is normally called the gas giant. It has 90% of nitrogen and also helium, some percentage of helium. We have Saturn that has also nitrogen, 75% and 25% of helium. We have Neptune and Uranus. The two also have hydrogen and helium that exists in their atmosphere. We know that all these planets where our planet Earth is a part of. So that's just to show you. Now the sun. I brought the sun especially because it's our special star, and the major energy input that we have on Earth is from the sun. So because the sun is also a star, and it has great influence on the Earth atmosphere and the processes that occur on the Earth, we have not established any other planets, but we won't doubt it also that other stars or even other planets do have influence on the Earth processes. So there's the sun. It has 70% hydrogen, 28% helium. It has some amount of oxygen, carbon dioxide, neon, iron, and some other heavy gases or metals. And we know the sun as the major input of energy to the processes of the Earth. And the radiation from the sun, like I said earlier on, every object, everybody gives off radiation depending on its temperature. So the sun also gives off radiation, and it gives off radiation as an electromagnetic radiation. It comes as a spectrum to the Earth, or just releases it, and the Earth receives it and uses it for its activities. So it determines the sun's energy or radiation determines the Earth energy budget as well. So whatever input we get from the sun, we get some absorbed in the atmosphere, we get some also absorbed by the Earth. And with these, the lot of control that we have. So we don't receive the same amount of energy from the Earth every time. So the energy from the Earth do vary from time to time. And studies has shown that, it very depends on the sun's activity. So the sun can go high in activity or can go low in activity. And our science studies have shown that the sun's activity correlates very well with the temperature of the globe, the Earth's temperature. So this is a plot showing solar cycle in red and the global temperature in blue. And so the trend is very consistent. So it's like the sun's activity has a lot of control over the Earth temperature. So this is just a really short presentation just to bring our minds on a lot of gaps that we have in our research in science. And we are asking ourselves a lot of questions as to how much, or in a way to quantify the effects of astronomy or the celestial activities on our climate system, because the Earth atmosphere is what we have our life on, and we live in, and the gases we have in the atmosphere, especially the oxygen that we breathe, the carbon dioxide the plants use for their food. I mean, how is it going to change in future? Are we still going to survive? Would little change or big change? Cannot tell. So this is a big study area and still controversial for discussion. But then it also comes to the fact that, so now if the stars are giving a lot of gases, especially carbon, it's a greenhouse gas. We have hydrogen, which can easily get combined with oxygen or ozone, and we get water vapor in the atmosphere, which is a greenhouse gas. And then hydrogen with carbon, we have methane. So if we have this combination, and these what the gases we get from the stars are getting right down to the earth, they may be far away, we cannot tell. So these are questions we are asking ourselves, and this is the new study area people are going into, and it's planetary sciences. So people are really going into such studies to determine how much effect that we have from these terrestrial bodies or astronomy into to influence climate change. I live here, but for those who may be interested, you may follow me. I post some of these natural issues and questions and mind-boggling issues on my social media handles. So you can follow me on Facebook, Instagram, YouTube. I have LinkedIn. You can just Google my name. I have a Twitter account. I forgot to put it there. So you can follow me, and then you pick one or two also information from there. Thank you very much.
All right, thank you so much, Dr. Nanama. That was amazing. I hope everybody enjoyed it. It's actually, like you said, a very new field, and I remember reading a few research papers on this, and it's very, very interesting and controversial, like you said. So thank you so much for actually presenting this way. I'm sure a few people have questions. So please, if you have any questions about what Dr. Nanama has presented, please, you can put it in the chat. And before we do so, just to congratulate you again on your promotion to associate professorship. So thank you so much. So let me check in the chat. Or Jemima, are you there? Can you check if we have?
Yes, I'm right here.
Yeah.
Okay. The first question is from Francis Adedeji, and he's asking, what is the effect of the surface pressure on Mars?
What's the effect of surface pressure on Mars? So
yes, please.
So Mars has its own pressure, and the Earth also has its pressure. So what does it mean, the effect of surface pressure on Mars? Is it the pressure of the Earth on Mars, or the other way around?
Oh, he says, what is the surface pressure, the effect of the surface pressure on Mars? I think he meant to say like the effect on Mars itself.
So the effect of Mars on Earth?
Just on Mars.
We can't be sure of exactly how much the composition or the atmosphere of other planets are having, but you can clearly see that what we have, like the composition of the atmosphere of the Earth, the gases that are available, the air, we have similar gases in other planets, except for Mercury, which doesn't have any atmosphere. We have all the other gases. All the other planets do have gases, but in terms of pressure, I cannot say how that's the effects of the surface pressure on Mars. I really don't know what you want to say, but the pressure on Mars is about 6 millibars or something, or 7.
I think maybe Francis, unmute and ask your question, because
maybe you can come clearer.
Okay, he said his place is noisy. Because again, it's confusing in terms of relating it to just.
But anyway, maybe if you want to compare, the Mars has very high surface pressure compared to the Earth. If that is, I don't know that's what he wants to know. I don't know. But anyway, maybe he can ask again.
Okay. So, Jemima, let's just
Okay.
move on to the other questions. If he can. unmute
Okay,
himself.
yes. Okay, while we wait for Francis, Josiah Fanini has his raised and he wants to ask a question.
Okay.
So,
I think-
so Josiah, the floor is yours.
Okay, thank you very much, Professor, for this session. My question is on the first plot you showed that has man-made effects on our global temperature. Not this last one, the first one.
Yeah, I
So,
remember. Like this one.
yes, this one. So my question is, this plot shows the year was from 1880 to 2020, which is about 140 years, if I'm correct. And we can see that in 140 years, we can only see 1.2 degree rise in temperature.
Exactly.
And
No.
so my concern is this should not be a cause for concern. I mean, 1.2 degree rise in temperature in 140 years. That and the second plot that shows solar cycle and how the sun's temperature changes the temperature of the earth kind of also showed that okay, apart from the effects of man, which is just 1.2 degree rise in 140 years or so. Now, the effects of the sun itself also plays a great role. If the sun becomes a little bit hotter in a cycle, the earth also feels hotter. So I'm just trying to say that this climate change should not be as big of an issue as everybody makes it, because this is not something very. So I want to hear what I want to know what to think about that. Is this not a very small?
I knew this was coming.
Okay.
Very well. Okay, so let me just explain. So if you say that from 1880 up to today, just 1.2 degrees warming, in the atmosphere, in the climate system, there's nothing like adjusts. There's nothing like small. There's nothing like big. It doesn't follow the logic like 1 + 1 = 2, or 1 - 1 = 0. In the climate system, 1 + 1 can be 10. 1 - 1 can be 20. So what it is that we don't have complete understanding of how the system works. And what we have known also from studies shows that a little change in anything can cause a bigger change in another. So you may say 1.2 is not degrees Celsius change, it may not be anything to worry about, but that can change the composition of a lot of things. It's like a glass full of water. So that glass may be full of water, as you will see and everybody will attest to. And then it may also allow you to add a few drops. So you only drop a little bit, drop by drop, and it will still contain the water. It will still be full, but still allow some drops. But remember that there can be one drop that will make the cup overflow. And if the cup overflows, it will not overflow only that one last drop that you put. It will overflow with many more drops. That is the situation we have in our climate system, or that's the way we kind of perceive the system. We can be sure the state where we are, whether it's full and it can still take some few drops, or it's really full and it's left with only one last drop, which doesn't matter, with like something like 1.2 is nothing. But that last one drop that we add may cause let's say the cup that's full to overflow. And as I said, it will not just overflow that one drop, but many more. So in all, we just have to be careful about how we do our thing. We just have to be measured in the way we live our life. We don't just have to hurt the earth. Well, we can clearly see that human beings are contributing to this. But where we try to even understand more is the influence of astronomy in our climate system. So that is where we are now. So that, as you said, we may not want to worry, or we should worry, or something like that. Yep.
Thank you very much. This is well explained. That explanation about a cup running over, that brings the kind of picture that I understand well. So thank you very much for that.
Okay, so it's the same. You're asking if the temperature is in degrees. So there's Celsius on one side and there's Fahrenheit on the other side. It's just the same.
Yes, I mean the second. This one is for this. The question is for the second plot of
the second one.
that shows the sun's period.
Going back to.
Yeah, I think it's the
Yes.
Yeah, it's. I think it's in degrees Celsius mostly.
Okay, thanks.
It should be in Celsius.
Okay, yes. Thank you very much.
Okay, I have
Josiah,
another.
Okay. okay.
Maybe let's take some other questions since you already have a few. Let's take some other questions.
Yes. Okay. All right. If anybody has a question, please raise your hand and then I'll get to you. But here in the chat, Kyosin wants to ask. He is wondering, how do scientists check for the elements found in the sun?
Okay, so in the sun. Okay, so there are the people who are doing solar physics. So solar physics is the study of the sun, and they have the, should I say, the technical know-how to take the measurements that they take. So there are ways to take these measurements. They have, different ways of taking the measurements. So some people, those who study like the solar cycle, for instance, they have a way of taking their measurements when the sun is happy and when the sun is sad. And they have a way of also measuring the element as well. Like the way we're talking about the star. So the sun is a star. We use telescopes, we use radio astronomy, we test the properties. So these gases that you see have different properties and they have different temperatures, they have different combinations. So we can use radio astronomy to determine the amount, the type of gas. And they do have different colors as well, remember. So they can use telescopes, especially radio telescope, to determine the color, the temperature, and other characteristics. Then you'll be able to categorize them into the different types of gases that they exist on those stars. So the sun also has a star, so it's the same thing. Okay. Any other?
Okay, thank you very, very much.
Yeah, that someone
And
else
now
asked a
Terry
question.
Azal, I'm sorry if I'm butchering
Yeah,
your name.
sorry, before
Terry has a question.
Yeah,
Yeah, so
before
Terry,
Terry.
the floor is yours. Unmute yourself and ask your question.
Okay, someone has a question in the chat, so it's fine. Okay, Terry, go ahead.
Terry, are you there?
I'm here. Thanks, Prof. As a student of astronomy, physics, I have a better understanding of most of the things she has presented. And what I am just curious about is the social media handles. Can she probably display that for us to take a look at it?
Okay. It's just my name on Facebook. Instagram is Ask the Prof. And then I have a YouTube. There's a link, Ask the Prof. So, thank you. There's a question in the chat as well.
Yes,
So,
King. Yes, King. Okay, he's asking. He's wondering. Any motivational words for ladies who want to pursue physics, astronomy, and space science?
Okay, before that one, there's a question on data science. So someone is asking, is data science used this field of study? Yes, I would say, and a big yes. So the two fields, whether climate science or astronomy, use a big data set or huge set of data. And so we do data science every time. Data management, we use computers, machine learning, and now even in climate science, we are applying artificial intelligence in supporting our modeling. And so we do use data science a lot. It's a big deal for us. So the motivation for women, for female, I don't know what you want to know as motivation, but I think that there are so many opportunities as in the challenges to bring solutions to, and that should be even your first motivation. The other motivation, which you will probably put as first, is that there are only a few of us in the field. And so once you show your interest to do, there are a lot of opportunities, there are a lot of engagement, there are a lot of doors that get open to you to take things up. But I tell you that the problems, the challenges alone should be a motivation for us to want to study this, and not just for women, but also men. But if you're a woman and then you have a discovery or you're able to be a solution to certain problems, you find something, it's a huge news. Yesterday, like this, social media was flooded about me because I'm kind of the youngest physics professor in Ghana, and also even the physics department. I'm the first female physics professor that has emerged at the Department of Physics at the University of Ghana. And so it's got so flooded on social media everywhere. It was about me. And that alone can bring some other opportunities also to you. I mean, once you write for grants fund and apply for scholarship here and there, you may be able to get it much easier. So, but first, the problem that we have to solve, the issue that we need to attend to should be a motivation for all of us to want to go into astronomy or physics or science or something like that. Thank you.
Yeah, thank you also. That was, I couldn't have imagined a better answer to that question. Thank you so much. Problems to be solved should be the reason, the pure motivation for everybody to join this course. Now, Benjamin has raised his hand. He wants, so Benjamin, please unmute yourself and ask a question. Okay, thank you very much.
Thank you so much, and for your wonderful presentation, Dan. I'm Benjamin Afagbeji. I'm a conservation architect and presently studying in Portugal. And what we do basically is to look at climate change vulnerabilities on cultural heritage sites, let's say historic sites and buildings. So climate change is really impacting heritage sites and causing a lot of damage to historical buildings, which I'm specialized in. So I kindly want Madam to assist if perhaps she has these indicators that they use to measure these impacts within zones, you understand, in terms of the volume of the effect within place, so that if we could have an idea about the equipment that they use on a large scale, because we take our recordings from the zone. When we get to the site, we take humidity, temperature, and all those things from within the site. But looking at her presentation, they're able to probably take data from a wider scope, which is very important. So I'll be very grateful to link up with her if she can help us with equipment that we need to take these vulnerabilities in a wider range, you know, outside of the local context within where the heritage site is located. I'll be very grateful. Thank you.
Thank you. So my contact, I brought it up again, my email and my number, it's on the WhatsApp. So congratulations for the work that we do. We are actually losing a lot of our cultural heritage sites. So due to climate change and also human activities as well. What we do is that, so you said you're able to take measurements when you get to the ground. Yes, we do the same. So even for the wider measurements, we still take from point to point and we put together. That is when we take in in situ measurement or take a measurement from ground, but measured with the instrument on ground. We also use satellites actually to take data from space. So we can take temperature data, rainfall, humidity as you are taking. So that helps us to get even wider coverage of measurements than the point by point measurement. So once we do that, we're able to we just need a good number of years, and it helps us to understand the present dynamics of whatever variable you're looking at. We are able to model to the past based on the behavior, based on the trend we have now. We're able to go back in years, and then we can also able to do the forward or future prediction as well. And then it helps us to understand whichever variable we are studying much better, and gives us the confidence our model is good enough. It helps us to also give confidence to the future prediction as well. So you can get in touch with me, and then we can have further discussion on that.
Okay, thank you so much. I very much appreciate it.
Thank you too.
Yes, then another question in the chat, Josiah. He's asking about the rising global temperature. How do we expect an exponential increase if we do nothing?
So Jemima, I think maybe you should add the last question too. We need to quickly.
And the last, yes, and the last question too says, is it possible for foreign students to work at the University of Ghana offline or online?
Okay, let me start with the last one. Yes, so we accept students from abroad. I'm currently with two students actually, but they are postdocs. So once your university will allow, we welcome that, and we collaborate with other institutions a lot. So we just make the arrangement and then find the way. Either you get funding, either we find funding, and then we just start work together. We do that. We allow student exchange programs. So on the first one, which is about the rising global temperatures. Okay, so if you say exponential increase, my answer would be kind of no for now, based on what we understand or how we understand. So it will have increase anyway. So probably not increase, but the change. So I say, whether human beings lived on it, the climate was going to change. The only problem, the challenge we have now about the climate system is that the rate at which it is changing, or the rate at which the globe is warming, is not natural. So if we allow the earth to do its natural things, then of course we expect every natural happenings to happen. But then our influence as human beings is causing the exponential increase, as you rightly put it. But then we are adding more to the rate at which it was supposed to happen has increased or has changed. So that is unnatural, and the earth will react to it, or is reacting to it in a way that we are seeing as the impact of climate or the extreme events that we are kind of experiencing is as a result of the unnatural changes the earth is going through. So it's kind of responding to, if human beings would just say stimulus or stimuli. Yep. We have
okay.
Yeah,
yes, there is one. This will be our last and final question. Unfortunately, our time is running. It's Terry Azaglo. You've raised your hand. Please ask a question. Make it quick.
Okay, thank you. So you mentioned climate change. Is there a way, instead of trying to battle, is there a way we can probably leverage on it for economic benefits?
Okay, so benefits we can, leverage on it is to probably use it as an opportunity to plant more trees. And those of us in the developing countries can probably advocate for funds to build our infrastructure adaptation structures, because we have a lot of forests. So that's actually a sink for carbon dioxide, which is one of the major greenhouse gases in the atmosphere. So once our forest is taking up the carbon dioxide in the atmosphere, and our activities that gives off greenhouse gases is much less, we can go to the global space and say we have carbon credit, that we need some money. It can be from the Green Climate Fund, it can also be from governments, some bilateral, multilateral agreement to get some funds to build our infrastructure. But it's also another opportunity is there's a challenge that we know. So it's an area you can easily go into to do your research. And that's whichever, I mean, your findings will be, can be a good contribution to knowledge, because we're really struggling to understand a lot of the processes of the earth and the impact and influence of the other terrestrial body on earth. So the little that you do, it's a big contribution to knowledge. It's another opportunity you can take advantage of here. Okay.
All right. So
thank you.
Yeah. So thank you so much for all your questions. Thank you, Jemima, for getting those questions here. And thank you so much, Dr. Nanama, for actually talking about this and also answering the questions. So I'm just quickly going to move on to the last part before we finish off today. So yeah, okay, let's share my screen now. Okay, cool. I hope people can see my screen now.
Yes.
All right, so I'm just going to talk about some of the things you can actually find, or if there's anything to actually see in the night sky. So these days it's not really night because most of the planets are visible in the morning. So the people who wake up early can actually be able to catch this. So tomorrow, which is 1st May, you can actually be able to see planets such as Saturn, Mars, and Jupiter, and even Venus too. And one amazing thing you will also be able to see is the conjunction of Jupiter and Venus. So, so on our night sky, it will look as if Jupiter and Venus are the same dot. Okay. However, you should know that, of course, they are millions of miles apart, but it's just because of the way they appear in the sky. When that happens, we usually call that a conjunction. So that's definitely something you should look out for. And also for the entire month of May, you will actually be able to see planets such as Saturn, Mars, Jupiter, and Venus just to the east. I think this is from Ghana, really. So if you're in Ghana, you should be able to see this. It will be slightly different from different locations on the globe, but just slightly before dawn, you should be able to see this. So this is a simulation from Stellarium, and you can actually see this. So you don't need a telescope to see this. These planets are visible to your naked eye. So one indication, so Mars will look red, which should tell you that that's the planet Mars. And those who don't know how to differentiate between a star and then a planet in the night sky, so we know stars usually twinkle, so they don't keep a steady light. They would seem like they're blinking. So if you see anything like that, that's actually a star. However, if you see something with a steady light, then that's definitely a planet. And if it's red, that's Mars. If you see very, very bright, that should be Venus because it's the brightest of the planets. So that's something you should look out for. And also, I think most of the month, again, you should be able to see moon passing by the planets towards getting to the end of the month. So these are a few simulations. So on the 22nd of May, around 5 a.m., you actually see the moon close to Saturn. The 25th, around the same time, you see it just passing the planet Mars and then Jupiter. And if you keep looking onto to about 27th, you would actually see that it will now be very close to Venus. And this is actually nice. So if you could do this, if you could wake up, I think it would be nice, take pictures on these various dates or these different dates. Maybe in our next section, you can show us those pictures. I think that would be great. So yeah. And then also, this doesn't usually, I think this is not something most people see. You usually look at the ISS, which is the International Space Station, but actually you can be able to see the Hubble Space Telescope, which is a space telescope. So not a ground-based telescope, but one that we have in space. And it's actually incredible because of the images it's been able to give us of our night sky. And there are a lot of amazing other pictures that if you want to see the Hubble Space Telescope has taken. So you can actually see this telescope as a dot. It will not be too bright as the International Space Station, but it will be bright and you can actually see it move. So It actually orbits about, I think, close to 15 times in about 90 minutes. And it will be moving at a speed of, I think, 8 kilometers per second. So it won't be too fast, but you will see it actually, move across the sky. And that should be, again, around dawn time. So around 4:57 to about 5 a.m. That's when you can actually see this. And I think we do have a simulation of how this will happen. So I'm just going to play this shortly, and you can actually see the Hubble Space Telescope move by. So this is it coming from the top, and you can see it's actually going to move almost across. So again, if this Stellarium app is very cool, and you can do all these things with it, and it's actually free. So it will be actually cool for you to do this also, of course, see it with your naked eye. Because of our time, I'm not going to make this finished, but you can actually see this move. So it seems to be moving very slow, but it's actually at about 8 kilometers per second, which is pretty fast and cool. All right, so to our announcements, and then I think I have one news to share. So coming up, we'll also be talking again with Dr. Naomi Asabre, and she'll be talking about the Ghana Radio Astronomy Telescope, or the observatory. She'll be talking about that. And then also coming up, we have a few other people who have confirmed that they would be speaking to us in the coming months. So these are things that I want people to look out for. So finally, if you're following our sections on the James Webb Space Telescope, it has now been able to complete its alignment. And all what this means is that, so it has different parts in terms of different telescopes. Some of them in infrared, most of them infrared. So these cameras have been, have been able to be, to complete their full alignment, which means that they'll be able to see the objects in the sky we want them to do. And this is a very, very huge step, because this means that we can move on to actually doing what we call the science instrument commissioning, which will just follow as being able to use the James Webb to actually look at far away stars, which actually tells us about the beginnings of our universe, really, and some other incredible details in terms of planets, if some of them could actually even possibly have life on them. So this is a very, very huge milestone. And you can see in this image, these various stars that you see there, these hundreds of thousands of these, and they actually belong to the Large Magellanic Cloud, which is just a small satellite galaxy in our own Milky Way galaxy. So this is great. I think I would send a link to some of these things so that you can visit and see these actual pictures yourself. But that should be it. So sorry if I rushed through this, but so this is the last thing I want to talk about. So I think before we finish and before people go, we can if you can turn your video on, will be cool, so that we take a group photo and then we can end today's section. So thank you so much. And if you could turn your video on, I think we can take it. So how do we do this? Okay, maybe somewhere there. So if you can take a screenshot, you should do so. I always struggle with this, but let me see. Okay, so okay. Yeah, I think I have most people now, so I'll take this part. Good smile. Take another one. People on the other side. Give us a minute. Okay. Yes. This is everybody. Yeah, I think this is everybody. All right. So thank you so much for joining our section and turning on your cameras for this. So I would say that if you have any more questions that you couldn't ask, I'm going to send email with the details of Dr. Nanama in terms if you want to make contact so that you can email her and then ask those questions. And then also this recording will be available on our YouTube page, which I think I would quickly share. Yeah, let me quickly share. So I think it's at Ghana Planetarium. Just a minute. Yes, I'm hoping you can see my screen. So it's at Ghana Planetarium on YouTube, and also GH Planetarium on Twitter. So I'll send all these details again in the email to everybody so that you can get in touch. So thank you so much for joining. Jemima, thank you so much for being here. Sarah had to be somewhere, so she couldn't make it, but I think she joined the section. So thank you so much. And thank you so much again, Dr. Nanama, and everybody who was able to join today's section. I think not just a part of today's topic, but Dr. Nanama has been very influential in getting astronomy and our food very, very, warming. So thank you so much again, and the great work you're doing.
Thank you. Hi, Terry.
Thank you, Paul.
Right, so bye, everybody.
Bye-bye.
Bye.